And thank you to the IJC for inviting me to speak here today. This is actually my first Inkjet Conference, and I have to say I'm really impressed by the scale and the breadth of this conference, and delighted to be talking. You stole my line. I really am the last thing between everybody here and lunch, so I will try and stick to time. This is what I'm going to be talking about this morning. Obviously, I'll give you an introduction as to who we are, but I think many of you are probably very familiar already with Sun Chemical. My focus is going to be packaging applications, and I'm going to take that applications perspective to try and help I think I said in the abstract, demystify. Not sure how easy it's going to be to demystify it. It is a complex area, but I will try. And then how we can help understand and look at the progress of inkjet printing in packaging. And I will be weaving in some key themes around chemistry, inkjet printing itself, and some of the print processing and end-use demands that packaging puts on us. So who we are. As I said, I think most of you know Sun Chemical. We're the world's leading producer of inks, coatings, and pigments. We have many employees, many installations around the world. We're part of the TheIJC group, so yeah, we have a very big weight in the packaging printing world. We have a lot of commitment to innovation, and really at this conference it's great to see all that being discussed. 17 R&D locations, a huge amount invested in R&D, and I've experienced that myself. I mean, I started at Midsummer Norton, which is the picture you see here, where Sunjet, which is the inkjet arm of Sun Chemical, is based. There were 6 of us in the lab in 1998 when I started there. There are now, 70 odd scientists working on inkjet R&D at Midsummer Norton. And I've put up there some of the key technology milestones on our development in inkjet inks in those 20 odd years. We aim to work through partnerships, and the key channel to market through us is through OEMs, as I think most of you know. We have a huge variety of inks that we develop and manufacture at Midsummer Norton, also in the US and in China. These are some of our brand names, customer-facing names for our products. And of course, the one I'm going to be focusing on is packaging inks in this talk today. So this is my intro slide. I put this up. It looks like quite a nice corporate slide. It looks very complicated. As I said, hopefully I can demystify packaging a little bit. It almost looks as complicated as Brexit, I have to say, but hopefully it won't be. This is how we can look at the application demands of packaging and try and break it down. I think the thing that people find particularly difficult is that, of course, and I think Mathieu touched on this, your printed packaging has to go through and tick every one of these, whichever is relevant to the application, and that's what can make it seem daunting, and I think for sure we're on the beginning of a journey for some of these applications in inkjet, no question. So the approach I'm going to take is I'm going to pick out one or two of these and explain a little bit in detail about how we see the demand and some of the progress that we're making in satisfying that. Now, I'm a chemist, so if you don't mind, I'm going to start with some ink chemistry. I may not pick out the ones you're most interested in, but hopefully I'll still give you some interesting background. Yeah, I spent the first half of my career in the analog packaging inks world. And this is just a quick look at the complexity behind printing, and again, I think Mathieu touched on this, using solvent-based flexo-engravure inks for flexible packaging. And you can see there are a huge number of different ink systems, and these are just some of the base resins that are used. There'll be flavors of these for different applications. And honestly, don't expect it to exist in the inkjet world. So this begins to hint at the need for primers and OPVs to make a single ink chemistry work, particularly aqueous ink chemistry, in these complex packaging applications. Another thing to think about is drying speed. You know, I mentioned in that slide before that in the analog world we're typically talking about fast drying solvent-based inks, ethanol, ethyl acetate, and this bar chart here really just shows the relative evaporation rate of these two solvents. And a lot of my focus in this talk is going to be about water-based inks. It's a relatively slow-drying solvent. So how you dry these inks is going to be of critical importance at production speeds. And this, just for comparison, is the sort of solvents that are currently used in inkjet printing, particularly wide format printing. So to help you understand a bit, and again I think Mathieu touched on some of these things, we sort of see almost like a direction in the development of our ink chemistries for packaging. And this isn't meant to imply that any one of these chemistries is better suited than the other in particular applications, but it's just a realistic attempt to identify how these chemistries have developed in terms of their time to market. UV and of course now UV and electron beam low migration inks are becoming well established for packaging label applications. We pioneered the development of aqueous UV inks a few years ago because the state of the technology then, it gave quite a good entry point into delivering an aqueous ink that could also be made durable, as Yuri explained, but had good, and we'll touch on this later, had good resolubility, so good reliability in an inkjet printing system. But now technologies are available, polymers are available that deliver some of those characteristics, and this is what we call functional aqueous, no longer any need to have a UV curing step in the drying process. Another way of helping understand that is to sort of picture it almost as a gap. So the vertical axis here is just some attempt to identify the range of applications that an ink chemistry can fulfill. As I mentioned, everybody wants the universal ink. They want a wide range of performance from an inkjet chemistry because you're not going to change the ink in an inkjet printer. And clearly energy curable is closest to achieving that. There's even a small gap here though. I mean, we're very familiar with the need to use corona treatment, for example, to deliver good performance in energy curable inks. Behind it is functional aqueous, and this gap is a little wider, and again this sort of hints at why we need primers and OPVs, as Mathieu explained, to deliver the right level of performance, as well as things like corona treatment. I do want to mention energy curing inks because, yeah, again, as Mathieu said, we do believe there is an application for energy curing inks in the packaging inks market, and I pinched a couple of slides from my colleague Damien Ward's talk a year ago, so apologies Damien, but I wanted to just bring out a couple of things because we know that, for example, the film weight is high for energy curing inks. These are 100% solids inks, and that may not be ideal for all the different packaging applications, particularly on thin films. We know that for UV curing, the latest printheads require lower viscosity inks, and I think that's come out in some talks yesterday. Low viscosity can be challenging to deliver the lowest possible migration in UV curing situations. And then there's the issue of curing very thick ink layers, particularly when you have a backing white. You get attenuation of UV light in the print layer. And of course, curing these low viscosity UV inks on uncoated and semi-coated papers and boards where you can get ink penetration, so the ink can no longer and particularly the complete penetration of the electrons in the E-beam process through thick ink films has the potential to deliver total cure in even situations where you have a backing white. And of course the no or little photoinitiator in these inks opens up the viscosity window in a very clever way, and we have, I have to say, some class-leading technology in this area. So back to our application performance demands. There's a little hint of some of the ink chemistry we're going to be talking about. I'd like to talk about reliability, of key importance in inkjet printing processes. Without reliability, some of these interesting aspects of inkjet printing around just-in-time and short-run delivery, they won't work. And I think, talking about aqueous functional inks, it's important to understand the drying process behind polymer film-forming aqueous inks, where you can almost see it as a two-step process. This first step, where you're going to a partially dry film, it is reversible if you choose the right chemistry and the right humectants and co-solvents. And this is going to be absolutely critical when you're talking about partial evaporation around the nozzle and on the nozzle plate. But of course you then want the polymer film to coalesce into a durable ink film, but only on the substrate. And here's some simple illustrations of what that means. This is really what we mean about resolubility. So you can see on the left here we just have a Petri dish of ink. We tip the Petri dish and allow a thin film of ink to form and partially dry, and then we swirl the dish around, and you can see how if you formulate the ink correctly, you can get complete resolubility of the ink in itself. If you don't use the correct materials, you leave a residue, and this of course would be poison around a nozzle and on an ink nozzle plate. And then it's very important that we deliver complete resolubility of the ink in the cleaning, aqueous cleaning fluid we're going to use to remove potential material on the nozzle plate during printhead maintenance processes. So this is just a kind of very visual illustration of what we mean by ink resolubility. We have to make sure that we have high quality and stable drop ejection. So these are just some drop watcher images of how we can contribute to developing optimized waveforms, for example, to deliver satellite-free printing at different grayscale levels at different frequencies. But of course, we also have to think about aspects that we call latency and open time. So that's how stable is the ink at the nozzle to either very short period pauses in firing, say between two patterns during the print process, or much longer periods of stoppage, the open time of the ink in the printhead. And clearly the ink chemistry and formulation has a lot of role to play there. And I think Yuri spent a long time looking at this. It's so important. Many of these latest printheads are going to be jetting aqueous inks. They have de-wetting coatings on the nozzle plate. Very important that we understand and control the potential chemical interaction between the ink and the de-wetting coating. And we're looking for the kind of performance towards this end. This is just these are just drops of water placed on pieces of nozzle plate material that have been soaked in the ink for a period of time. Of course, we should remember that it isn't just chemistry that can affect the de-wetting coating. The way in which the printhead is maintained, any kind of physical process, can also have an impact, and that comes back to good resolubility and the ease with which we can remove any partially dried ink. So back to our application performance demands. Where are we going to go next? Image quality. I'm sure a lot of you are thinking, yeah, this is how are you going to achieve good image quality with aqueous inks? Here we come back to primer. You know, the range of surface energies of flexible packaging substrates, plastic flexible packaging, are very wide, even when you've applied a corona treatment. And of course, these different kinds, polyester, oriented polypropylene, low-density polyethylene, they have different levels of surface additive to control things like blocking and slip. And even with corona treatment, some of these additives are not entirely removed. And then, of course, you have uncoated, coated boards with very different surface textures and absorption levels. So here's just one example. So this is an ink drop on polyester film, corona-treated polyester film. This is plain polyester. Within 500 milliseconds, the drop has completely spread. If we can get the primer chemistry right, we can control that spread, tune that spread in a way that delivers good image quality. And this is with a primer that is typically less than 1 gram per square meter dry primer here. And these are some prints from some of the early work we did in this area. But the point I'm trying to make here is that one of the roles of the primer is to allow a printer who's printing on a diverse range of substrates to achieve a kind of harmonized image quality on very different surfaces. And you can sort of see that here without any primer. Particularly on polyester, you get very excessive spread and intercolor bleed. If you can start to get the primer chemistry right, you can start to see that the image quality can be harmonized across very different surfaces, widening the application potential for your inkjet packaging printer. So in a way, this is how you can see the sort of different legs to a primer formulation. You know, you need the primer to help with adhesion. You need the primer to help a little bit with the drying of the ink. And you also need the primer to help fix the ink. All three of these are important, and they can come from different materials in the primer, or single materials can deliver 2 or 3 of these in one go. And I just put some photomicrographs down at the bottom there of how the drop control changes the appearance, for example, of the different tones in a print, depending on the level of fixation that you've built into your primer. And really what you're looking for is the middle level there, where you're getting this good trapping of one drop over another. You're getting a good balance of control and fixation. And again, this is with primer technology that is less than 1 GSM dry on the film. And this is the latest situation of what we're able to achieve under realistic production conditions. So this is reverse printed on polyester film with some of our latest primer technology, and you can see the level of control and image quality achievable. Matthew mentioned that, of course, flexible packaging is a white world. 50% by volume of ink, typically a flexible packaging printer will use, is white, mostly transparent films. So we're looking at applying our Flexo aqueous white lamination ink technology. You can see how the print then becomes visible even when placed over a black surface. And of course, eventually on our roadmap is a digital white, but one step at a time. And of course, when we talk about aqueous inkjet inks, intercolor bleed always comes to mind, and we can see how a change in primer chemistry can help control and influence intercolor bleed, and also mottle. Here we have a coated board with no primer, a coated board with one of our latest primer technologies, and you can see how even though the ink apparently wets the primed surface less well, it's the chemical interaction that helps deliver this uniformity, this homogeneity in the coverage in a way that unprimed, without any chemical control, you don't get. So back to our application performance demands. I think drying has to be something that everybody must be thinking about with aqueous inkjet at production speeds. We know that we're not going to achieve sufficiently fast drying of aqueous inks with hot air motion alone. It's going to be a key component, but we are going to need some infrared. That's very typical of drying systems that are out there today. So I'm just showing you here, this is the infrared spectrum from, if you like, the visible end to mid-infrared of our wet inks, our CMYK wet inks. And if I overlay, for example, the energy distribution by wavelength of a near-infrared lamp, which is typically running at a temperature of 3000 Kelvin, you can see how the peak emission and the emissions just down to short absorption of energy by pigments. But there's clearly a lot of energy also in some of these longer wavelengths, which is where water absorbs, and peaks here in the infrared. And then here are the mid-infrared lamps that again typically used in infrared drying systems. Here these typically run at 1200 Kelvin. The peak wavelength is obviously much longer. Again, now you're making very good use of these peak absorptions by water. We do have to be mindful of the substrate, of course, and this is going to be definitely a challenge for drying aqueous inks on plastic films. They do have a significant absorption that increases to longer wavelengths. And this, we're going to have to learn how to manage this, how to optimize systems to deliver acceptable print speeds on a range of different films, which may have differing heat sensitivities. BOPP is much more heat sensitive than polyester. Don't underestimate the role of the primer in drying of the print. So here this is a very simple, this is a very simple visual, if I can get back to it, where all we've done is we've drawn down a primer in this area, a less than 1 GSM primer in this area. We've then drawn down over it a 6 micron ink layer, and then we've just under roller pressure applied another film over the top, peeled it away and looked at that, what comes off on that film. And you can see that with just a short warm air dry, so essentially the ink, as you can see, most of the ink is transferred onto the applied film. Where the primer is, there's no transfer at all. And this again is a less than 1 GSM dry coat weight of primer. clearly the final print has to have some sensible end-use application properties. Lamination is, I think, a critical one, and we're already looking at how the primer chemistry and choice can allow us to deliver sensible peel strengths, sensible lamination bonds with existing lamination adhesives. And primer and ink chemistry working together are absolutely critical in enabling us to deliver a sensible level of lamination bond. And we mustn't forget this complex world of flexible packaging. You know, this is a vertical form fill seal machine preparing maybe things like crisp bags. Think of the demands it places on the print. You know, the print has to slip over this collar. It has to resist transfer onto the heat sealing jaws that are in here. And of course, in the traditional print world, all of this is typically and have to build into our inkjet print. And again, this hints at why we think OPVs are definitely going to be critical in helping deliver some of these characteristics. Finally, let's think a little bit about regulatory compliance, which was definitely touched on very well by the earlier presentations. It's definitely a challenging regulatory landscape, no question, for any of those ink technologies, UV, electron beam, aqueous. You know, there are legal requirements. So you've got the European Framework Regulation on packaging, you have the Swiss Ordinance, of course you have chemical registrations in different national territories. You have industry regulation, so we're members of the European Printing Ink Association, and that places very sensible constraints on the nature of raw materials that we can use, good manufacturing practice to ensure that we're delivering the same ink every time. And then you've got corporate restrictions, and these were both mentioned. For example, Nestlé guidance, very well known definition of the kinds of materials that you cannot use in inks for food packaging. Tetra Pak S009 list as well was mentioned for liquid packaging, and these contain negative lists, concentration limits, and aqueous inks have to meet these requirements just as much as inks. And you know, of course, the correct choice of substrates is critically important for UV and the electron beam. As I mentioned, you don't want too much penetration of ink into the substrate. But even for aqueous inks, we're going to have to think about, are we drying the ink sufficiently to remove all of the volatile components that could migrate? And I think, Mathieu, you mentioned the very low migration levels that can be applicable depending on the level of toxicity testing that exists for the raw material that's been used. So how do I sort of bring all that to conclusion? I hope I've shown you that you know, this is real. There are really challenging applications out there, but there are some real developments going on that I think, you know, can show that in the future, hopefully, we're going to be able to meet these challenges. So yeah, we believe energy curing and aqueous, they can both provide solutions in the packaging area. I'm not trying to show by this presentation that energy curing inks are not being considered. Of course, aqueous has significant attractions. Let's not underestimate, there's still a lot to learn. If we can understand the application performance properties that we need at every stage, bring them together, we mustn't forget anything, then we will deliver a successful package. But it's going to require cooperation between all the people at this conference to deliver a successful solution. Any questions? Thank you very much.